Hello everyone, welcome back. This is Mr. Cobalt, and in this video I'm just going to summarize everything I've kind of talked about in previous videos regarding periodic trends. So the first thing is, don't overthink this stuff. If you overthink it, you can talk yourself backwards into answers that don't make sense. So just focus on the fact that there are only a set number of trends to learn, and practice explaining each trend until you can do it in your sleep, right? So if you practice explaining it to other people, then you'll learn it better, and then you'll be able to understand it more deeply, because being able to explain it well to someone else really just show you that you've learned the material. And there are always going to be exceptions, right? So don't be bogged down by the exceptions. So don't worry about that. Just focus on the overall pattern and answer questions based on patterns, not based on like whether or not there's an exception to the rule or not. Okay, so let's talk about periodic trends. So the factors that contribute to periodic trends we see in the periodic table. So we're looking at factors that contribute. So everything is about attractions and repulsions. Remember what I talked about in an earlier video. It all boils down to Coulomb's law. And the two factors that are involved in Coulomb's law is the size of charges, right? So bigger charge means, stronger attractive forces or stronger repelling forces or repulsions, right? And then the second factor in Coulomb's law is distance between the charges, right? So farther away you are, the less attraction or less repulsion. The closer you are, the stronger the attraction or stronger the repulsion. So we're looking at how far the charges are from each other and how big these charges are. So let's review a little bit about the shielding effect. Remember, the shielding effect is due to the inner core electrons are shielding the nucleus from the outer valence electrons. And so what they're doing is they have a repelling force on each other. So the inner core electrons are repelling the outer valence electrons. And so that repelling force by the core electrons kind of cancels out some of the attractive force by the nucleus. And so the valence electrons end up not feeling as strong of attractive force. So that's what shielding is all about. So this keeps the valence electrons from feeling the full attractive force of the nucleus. And so what we then need to calculate is what is called the effective nuclear charge. Remember, so the effective nuclear charge is the relative attraction that the valence electrons have for the protons in the nucleus. So they're not really feeling all of the protons in the nucleus. They're feeling a portion of it. So it's relative to the number of protons that they can actually feel. And so the way to understand this is that for every proton that attracts, you have like a 1 plus charge. Every core electron that is shielding is going to cancel that out. So you can kind of do the math. And then what's left over is what would be the effective nuclear charge. So when we're talking about effective nuclear charge, we're adding a proton. Every time we add a proton, we also add an electron to balance the charge in our neutral atom. And so when we add a proton, that's going to have a larger effect than adding an electron into the valence shell. So when we add an electron into the valence shell, there is going to be some repulsion there because negatives repel each other. And so that is going to have somewhat of a shielding effect, but that shielding effect is not going to be a big deal compared to the proton attractive force, right? So adding a proton is going to have a larger effect than adding a valence electron. And as I showed in my other videos, as you go across the period, the number of core electrons and therefore the amount of shielding does not change. So the number of core electrons does not change, and therefore the amount of shielding really doesn't change from the core electrons. And again, adding that one valence electron extra adds a little bit of repulsion, but again, adding that proton is going to have a bigger effect. So you can see here on the tug of war, adding the really big people on the left is going to have a larger effect on the tug of war analogy that I talked about versus adding another small electron to the other side. So that's kind of part of the analogy. And so when we're calculating the effective nuclear charge, this is the equation we're going to use. So the effective nuclear charge, or ZF, is, again, the relative attraction of valence electrons have for protons in the nucleus. So that effective nuclear charge is going to be equal to Z, and Z is the symbol that we use for atomic number. So the atomic number Z is the number of protons. So that's the number of protons in the actual nucleus. And then we're going to subtract the S, which is the core electrons, the inner electrons, and they're going to be shielding the nucleus. So you can think of S as shielding electrons or inner core electrons. So the number of core electrons, we're subtracting that from the total number of protons. And so therefore, that's going to leave us with a certain number of protons that aren't shielded. And that's the effective nuclear charge that the valence electrons are actually feeling. And so here's a couple of examples. So you have magnesium. Magnesium is number 12 on the periodic table. And so that's going to have 12 protons. So that's going to be your Z. And then we notice that the core electrons in that magnesium atom is going to be 10, right? We have two inner shells, two energy shells. The first one has 2 electrons. The second one has 8. So that's going to be a total of 10 inner core electrons. So then 12 minus 10 is 2. So 2 is the effective nuclear charge felt by the valence electrons in magnesium. Aluminum, we could do aluminum. So aluminum has 13 protons. So it's number 13 on the periodic table, which is the atomic number. And then we have the S, and again, the S stays the same because aluminum and magnesium are in the same period. So the number of core electrons stays the same. So it's, again, 10 electrons. We have 2 electrons in the inner shell, and we have 8 electrons in the second shell. So first shell, 2 electrons, second shell, 8 electrons, that makes 10. And so here we would do Z minus S, 13 minus 10 gives you 3. So here in aluminum, because of that extra proton that was added to aluminum, the valence electrons for aluminum feel a larger effective nuclear charge, a positive 3. So aluminum is smaller, right? So if we're looking at the size of the aluminum versus size of magnesium, we learn that, okay, larger effective nuclear charge means that the charge is larger. So we're going back to Coulomb's law. Coulomb's law says that, like, larger charges are going to have larger effect. So if the effective nuclear charge is larger for the aluminum, then that's going to attract more strongly the electrons. And so they're going to be pulled in closer to the nucleus. And so aluminum would be smaller than magnesium because magnesium's effective nuclear charge is not as big, so it's not attracting the electrons as strongly, and so not pulling them in as close as they are for aluminum. Okay, so we're going to talk about atomic radius. So let's go on to atomic radius. So what is atomic radius? So atomic radius is 1/2 the distance between the 2 bonded nuclei. So if we go back here, we can't really measure the atomic radius of an atom. So we can measure the bond length of 2 homonuclear atoms, or atoms of the same type, so 2 hydrogen atoms. And so we measure that bond length, and we just cut it in half. So that would make the radius, half of that would be the radius of your of your hydrogen atom. So here we have two hydrogens bonded together. You can find the bond length between them, and then once you find that, you just divide it in half, and that becomes the radius of one atom. So the atomic radius is 1/2 the distance between two bonded nuclei. And you can't measure to the edge because orbitals aren't tangible things. So it's not like we can actually measure an orbital length or anything like that. So, so when we're talking about atomic radius, so how does the atomic radius change? So the atomic radius is going to change as you go down a group. The atomic radius gets larger, and as you go from right to left, it's going to get larger. Or if you want to think of the other way, if you go up a group, it's going to get smaller, and if you go from left to right, it's going to get smaller. So the general trend is that it increases going from the top right to the bottom left, or it decreases going from bottom left to top right. Either way is fine. So then the question is, well, why? Why does it increase going down a group? So it increases going down a group because of the increased shielding, right? You get more electrons in the core electrons, right? More energy levels are in the inside, so that's more shielding. But I think more importantly, you'll notice from my earlier videos that you notice that the effective nuclear charge doesn't really change all that much. So remember, when we're talking about Coulomb's law has those two factors: the size of the charge and the distance that the charges are separated. So in this case, when you're going down a group, the size of the charges aren't really changing. So when we're looking at effective nuclear charge really isn't changing all that much. And that is because of the increased shielding, and that cancels out the increase in the number of protons. So even though you're increasing the nucleus by a lot, you're also increasing the amount of shielding as well. But also, more importantly, you want to think about it as the distance from the nucleus. So you're adding another energy level, and that added energy level, those electrons are farther from the nucleus. And so that distance is going to cause a weaker attractive force. And so they're not going to be held as closely together. So there's less attraction there, and that's because of the distance. They're farther apart. So here, why does it decrease to the right? And again, here we're talking about increased nuclear charge. So we saw in an earlier video that when you go from left to right, you're increasing in the effective nuclear charge. And so there, when we're thinking about Coulomb's law, we're thinking about the size of the charges. So the size of the charges are getting bigger. The nuclear charges are getting bigger. And so stronger attractive force, it's going to pull in the electrons more. So they're going to come closer, and the atom's going to be smaller. So when we're talking about ionic radius, when we're looking at cations and anions, and again, I covered this in an earlier video, when you lose electrons, the cation is smaller than the normal atom, the uncharged neutral atom. And this this reduces electron repulsions, right? So when you take electrons away, you're reducing the electron repulsions. There's less electrons repelling each other, and this may drop down and to an energy level as well. So the atom is getting smaller. Anions, they're gaining electrons, so the anion is always going to be bigger than the neutral atom. And again, that's because when you add extra electrons, you get more repulsion, so they're repelling each other more, and thus it's making the atom get bigger than the neutral atom. So when we're talking about isoelectric species, this is where the atoms and ions all have the same number of electrons. That's what means isoelectric. So iso, same, electric is referring to electrons. So isoelectric, they have the same number of electrons. So when you're comparing atoms and ions that have the same electrons, they're all going to have the same electron configuration. And so the difference between the elements and the ions is going to be the number of protons. So if you got the same number of electrons, then the shielding is going to be the same. They're not going to differ in shielding. So the only thing that's going to differ is the number of protons, which is going to change the effective nuclear charge. So here we're looking at effective nuclear charge. And so because oxygen has 8 protons, it's going to be, those 8 protons are not going to be attracting the electrons as strongly as, say, fluorine that has 9 protons or neon that has 10. So as you increase the number of protons in the isoelectric series, then the atom would get smaller because you've got greater attractive force or due to the greater nuclear charge. Okay, what about ionization energy? So ionization energy is, remember, the energy that's needed to remove an electron from a neutral atom, your first electron from the neutral atom. And so if you have high ionization energy, then it's going to be harder to pull away the electron. If you have a lower ionization energy, it's going to be easy because it doesn't take a lot of energy to remove it, right? So you can see here in this picture. So ionization, what is it? The energy required to remove an electron from a neutral atom of an element. Okay, so the ionization energy we see increases as you go up a group, and it increases as you go to the right of the period. So the noble gases are the highest in ionization energy. And that's the reason is because they're stable. They're the most stable element. They don't want to get rid of electrons because of their stability. So the general trend for ionization energy is that it increases going from the bottom left to the top right of your periodic table. So why does ionization energy decrease going down? This is because, again, you have increased shielding. So as you go down the group, you're increasing the shielding. Again, the shielding is increasing because you're adding more uh, energy levels to the inside core of your atom. That's going to be between the valence electrons. But again, I think the more important thing to keep in mind is that the effective nuclear charge is not changing because even the added shielding is canceling out the extra protons that are put in there. But what you see happening as well, that is kind of, I think, more important to see, is that you're getting an increase in the number of energy levels. So the added energy level, those electrons, those valence electrons, are farther from the nucleus. So that distance between the nucleus and the electrons is really affecting the attractive force. And so they're not going to feel as big of a force. And so it's going to be easier to remove them. It's not going to take as much energy. So it has a lower ionization energy. When you go, when you're going from left to right on the periodic table, the ionization energy is increasing because there, again, you're looking at an increase in nuclear charge. So you're increasing the number of protons, the effective nuclear charge is increasing, and therefore the attractive force, because of, again, Coulomb's law, the bigger the charge is, the stronger the attractive force, and it's going to take more energy to remove the electron when you have to overcome a greater attractive force. And so when we're talking about subsequent ionization energies, right, this is where you're removing one electron at a time from the atom. Your first electron may require a certain amount of energy, and then your second electron requires a little bit more. And then at some point, you get this huge leap in ionization energy. And the reason for that is because the first electrons that you remove are from the valence electron shell, the farthest shell, the outermost shell of your atom. And so because they're the farthest and they're the shield, there's not a lot of pull on them. And so it's easy to remove those, right? So here we can see for sodium has one valence electron. So the first electron, you only need 496 kilojoules per mole to remove that. And then the second electron is your first core electron. And you can see there's like almost a 10-fold difference. It takes 10 times as much energy to remove that first core electron than it did that first valence electron. And the reason for that is because your core electrons, the next energy level is much, much closer to the nucleus. And so it's feeling a much greater pull. And there's less shielding as well. So there's less energy levels between the electrons in this energy level than your valence shell. So what about electronegativity? So electronegativity is how much the electrons are going to be pulling, or how much the atom is pulling the electrons in a bond. So these are bonded atoms pulling on their electrons that are shared. So electronegativity, what is it? It's a measure of the ability of an atom in a chemical compound to attract electrons from another atom in the compound. So basically, it's saying how strongly can one atom pull on the electrons being shared in the bond. So we saw that in the picture. So in the periodic table, we saw that the trend is that the electronegativity increases going up a group, and it increases going from left to right. So the general trend is going from increasing from the bottom left to the top right. And so why is that? So again, we're looking at either shielding or nuclear charge. And so when we're looking at electronegativity, there's a decrease. It decreases down a group because of, again, you have this increased shielding, you have this added outside shell. And again, the valence electrons are now farther from the nucleus. There's no increase really in the effective nuclear charge. So it's not an increase in charges. So it's an increase in distance, right? Again, we're thinking Coulomb's law. Either we're looking at an increase in charges or we're looking at an increase in distance. Here we're looking more at an increase in distance because we're adding that extra energy level to the outside. We're getting farther away. There's more energy levels on the inside shielding the nucleus, even though the nucleus is like bigger. So that's the reason why we don't see really much of an increase in the effective nuclear charge going down a group, because not only are the protons added, but you're adding more core electrons that cancel out those protons. So it increases to the right, electronegativity increases to the right because of increased nuclear charge. So as you're going from left to right, the effective nuclear charge is increasing. Those higher charges cause a higher attraction. They want more electrons. So they're going to pull on those electrons more. They're going to want those electrons more because there's just a higher effective nuclear charge. Whereas electrons that are closer to the nucleus are going to be wanting, the atoms are going to be wanting those electrons more because the energy level, the valence shell is closer. So if we go back to this one, again, the valence shell is closer to the top of the group. And so that means that they're going to want to attract the electrons stronger on the top than on the bottom. And here it's charged. So the stronger the effective charge, the more they're going to want to pull on those electrons in the bond. So what about reactivity? Reactivity is a little bit more hard to, it's tricky to do. So here we're talking about elements and how they react. Elements that are in the same group have similar types of behaviors because they have the same number of electrons. That is really important. So it's the number of valence electrons that determines how they react, what their behaviors are, what their properties are. But the magnitude of the reaction changes based upon whether you're on the left or right. Metals and nonmetals have opposite trends. Noble gases are inert. They're not reactive at all because they are stable, so we ignore them as far as reactivity. they're just not reactive. So why is it that metals increase in reactivity going down, but nonmetals increase going up the group? So metals increase down because, again, we're looking at this issue of increased shielding, but really it's not increased, it's decreased shielding. So that's a little bit tricky there. So what's the best way to think about this? So you have fewer energy levels. So when you're going down a group, so here we're talking about metals, right? So when you go down a group, what's going on? So again, the atom is getting bigger. You're adding more energy levels. The electrons are getting farther from the nucleus, so there's not as much pull on the electrons. So what happens? It's easier to remove electrons. And it's the ease of removing electrons that makes it more reactive. So so that's what's going on with regard to the metals, or the metals want to increase. So the easier it is to get rid of their electrons, the more reactive it's going to be. So when you go down a group, the reactivity of metals is going to increase. Okay. So let's see, that's for metals. Now for non-metals, so this slide here, this is for non-metals. Sorry if that was confusing. So this is for metals. What I was just explaining was for metals, and this is for non-metals. So when you go up a group, it becomes more reactive. Why? You got to think about what metals and nonmetals want. So metals want to lose their electrons, be like noble gases. So going down a group, it becomes easier to remove electrons, and that's what they want. So they want to lose the electrons. For nonmetals, nonmetals want the electrons. They want to pick up the electrons. So if it's easier to gain the electrons, that's going to make them more reactive. And so when you go up the group, the electrons, the valence electrons are closer to the nucleus. They're going to feel a stronger pull. They're going to want the electrons more. And so it's going to be easier to gain electrons when you're at the top of the group, because the electrons are closer to the nucleus. They're going to feel a greater pull. So it's easier to gain electrons. Therefore, they're going to be more reactive. But when you go down the group, the valence electrons are getting farther away from the nucleus. There's not as much of a pull. So gaining the electron is not going to make it any more stable. So they're not going to be as reactive. So that's why going down a group for the nonmetals decreases reactivity, but but going up, it increases. So it's the opposite of metals. And so a quick summary, here's a quick summary of the trends. So make sure you know this for your class. And so here's another example of these intermediate forces. So if we're comparing lithium and cesium and iodine, we can kind of see which one's going to have a smaller Z effective or a smaller distance between them. And you can kind of compare the electronegativity of various elements on the periodic table, or ionization energy. So you can compare elements on the periodic table and say, okay, which element is going to have a higher ionization energy, which one's going to have a higher electronegativity, which one's going to be a larger atom, and so on. So if you know the trends, you can then compare what elements are on the periodic table. Okay, and so that's it for this video.